Yes, Keanu, you are my favorite student. For the next nanosecond. Yes, reporting. The best made right now, this moment, you're the best made student right now.
That's unfair.
Is it?
It really is.
Why, Nick?
I'm the most respectful student.
You are very respectful. Yeah. All right, anyways. Let's start with just doing a little recap of the last video we saw on the origins of the universe. And so what did we learn? Where are the elements made? In the sun and the stars, right? So how many of you guys knew that before you watched that video? Not that many of you. So those of you who didn't know that, where did you think the elements came from?
They just were made up.
They just were here.
They were just here and no one... Did you guys ever give it a thought?
No.
Oh, come on. All right, you need to. All right, you need to be curious about the environment around you. All right, elements are made in the stars, but not all of them, right? Which ones are made in the stars?
1 through 92.
1 and 92. Are there exceptions?
Yes.
Yeah, what are the 2 exceptions?
Stuff.
What do you mean stuff? Yeah, Patrick. Number 43 and number 61. You don't have to really know what they're called. Just give me a number, right?
Actually, they're called...
Technetium and promethium.
Technetium and promethium.
Oh, nice. You can pronounce it. Good. All right. Now, our sun makes numbers 1 to 26, right? It doesn't make all 92. How come? The video told you. Patrick knows. Look, he's got a smile on his face. Yeah? Yeah, you. Right, so it can't fuse anymore because the temperature and the pressure isn't high enough to keep going. And on top of that, iron's very heavy. So it'll sink to the core of the star, it collapses on itself, and then it implodes. What is that called? Yeah, Sarah. It's a supernova. All right, so our sun makes elements 1 to 126. Stars have to implode or become supernovae to create sufficient temperatures and pressures to make numbers 27 to 92.
Why is it supernovas?
Novae for plural.
Yeah, I know. But why is it supernova?
Because it's all based on Latin, and that's how you do the plural for Latin. It's caliente enough for you? All right, so elements 93 to 118 then therefore have to be man-made. Okay, so who was the first guy to start making these things? Seaborg, the guy who gave us the F block on the periodic table, right? So Glenn Seaborg, who was only able to make 93 to 102. Hey, what are you making that sound for? That's it? That's 10 elements. More than you've made.
I've made 15.
15 elements?
Yes.
We all carry one in our back pockets, right? A big particle accelerator. It just happens to be like a building with a piece of equipment that's like a mile wide in radius. Is it in your pocket? Costs a couple $1 billion to build.
That's thrown around.
Yeah, that is, right? Listen, I hope one day you have that kind of money. It'd be great. The Flash? That's all you aspire to be, is the Flash? What's that? Yeah, I figured.
This is on recording.
I know, right? It's on recording. The attitude. The love in the room. All right. Okay, so what did he do? He studied uranium, because remember he worked on the Manhattan Project on the atomic bomb? And he took it and he just shot it. He put it in the beam. That's in the particle accelerator. And he basically put it in line of fire of a proton beam. All right. And so, like, if you have uranium and you add one proton to it, and that manages to stick to the nucleus, what does it become? NP, Neptunium. Right, because for a while there they were naming them after the planets, right? So uranium after Uranus, plutonium after Pluto, right? Neptunium after Neptune. After like those, yeah, I guess Mercury.
After America, right?
Yes. All right. So elements 92 to 94 they named after planets. After a while they started naming them after places, particularly places where the things were created. So 95 is Americium, like America. Like 97 is Berkelium, because the group that did it was from Berkeley. 98 was Californium, because one of those facilities is in California.
99 is Einstein.
I know. For a while there, they got tired of naming it after places because it was getting kind of dull. Because I think partially because all the places they were naming were American places. So the international community didn't really like that, right? So then they started naming them after scientists. So then we have 99, which is Einsteinium, 100, which is Fermium, 101, which is Mendelevium, 102 is Nobelium, 103 is Lawrencium. Yes? No. I'll get stuck. I can get most of them, but I'll get stuck. Then, 104 Rutherfordium, 106 is Seaborgium, right? 109 Meitnerium. So they liked a lot of the big scientists of the day. And then 111 Röntgenium, 112 Copernicum. And then somewhere in there they kind of got tired. They went back to naming them after some places. So 114 is Florovium, after the city in Russia where that Russian group did it. Or 110 is Darmstadtium.
Yeah, you're pronouncing that wrong. It's actually Darmstadtium.
Am I really pronouncing? Well, I'm pretty sure I took 5 years of German in college. I think it's Darmstadt.
No one cares.
But anyway, so they kind of went back and forth between naming them after people, places, and things, right? All right, anyways, if you get 2 protons to stick, you make plutonium. If you get 3 protons to stick, you make americium, and so on and so forth, up until you get to element number 102. All right? And about 102, hey, some people care. It's a good party trick.
Definitely not.
Oh, you know German, good job.
What's that?
No,
Germans care.
they really?
Yeah.
Steven Schleichen.
Well,
9.
9 is not the
See,
number.
Kyle?
Hey!
You're
Inappropriate.
German though, what does that mean?
Inappropriate.
What does it mean though?
Don't worry about it. Okay. All right. Anyways.
What do you think?
Okay. All right. Count it. Deep breath. Take a step back. Step away from your mouth. There you go. All right. Okay. So this process stopped working after elements number 102 because the nucleus got just too big. Yeah.
So the person who created all the elements, what are the elements that Fred Seaborg?
Seaborg.
Yeah. Why did he just keep adding more? Did Fred person before him just keep adding more protons?
If you pay attention to the video, it said that it stopped working.
No, before 102.
No, I don't hear it. Watch the video.
Because before 102, you found them in nature. You can just mine them out of the ground.
Okay. So why didn't they just find them all and name them after one person?
We talked.
I think they just found them all. How
What do you mean they can find them all?
You said they found them in nature.
Yeah, individually.
Oh, okay.
Well, some are. A lot of those things were discovered. 75% of the periodic table was discovered before, or right around the time Mendeleev came up with his periodic table.
Yeah, so why don't you shut your...
Hey, be quiet.
Let's use it on
All right. Anyways, it is recording. All right. Anyways, the nucleus got too big. The nucleus became too proton heavy. And when I say heavy, I'm not talking about weight. What I mean by proton heavy is that it had too many protons, and 2 protons have what kind of a charge? Positive charge, and what do 2 positives do to each other? They repel. So there's too many protons that are repelling each other, causing the nucleus to fall apart. So you remember that graphic? They depicted the protons like big muscle heads. So 2 muscle heads in a room together, what do they want to do? Fight. All right, which is fighting. Here's the other problem. Up until this time, we didn't even know the neutron did. As a matter of fact, they discovered the neutron in the process of doing all these experiments. And the reason why the neutron was so elusive, right, you couldn't find it, was because most of the experiments that they did, like Thomson's experiments and Rutherford's experiments, were looking at things that had charges. They used magnets to try to detect things. Neutrons don't respond to magnets. Yeah, Patrick?
So if they were finding uranium, assuming that's uranium neutrons, they made a scale of 100 to protons and 100 to electrons.
You can use the ions of them to get the right number of electrons too. The electrons aren't what they were focusing on here. It was just the protons and the neutrons. Yes, Evan. Caleb, turn around. To make 184?
Sure.
I don't think it would stay together. Okay, and I'll tell you why in the next sentence. Yeah, Nick.
You forgot the other,
What? What did I forget?
Yeah.
Oh, did I forget out where?
yeah.
Does it bother me? I'm sorry. I know how much. Here.
That's so unprofessional.
You're really criticizing my use of parentheses? Listen, Stinker, I'm in control of your grade book. All right, next. Okay, so the neutrons, as we found out, stop the protons from repelling each other. Remember, those are the little graphic things that look like little nerves. They get in between the protons and they keep them from fighting each other. It's that pacifist in the room, right? No fighting. Hey. He's going to break you in half. He's like a foot taller than you.
According to your us,
Yeah?
alright?
Yeah.
Where are they on campus?
On eCampus, on the modules.
I don't see it. I want to see it.
Yeah.
I just want to make sure.
You want me to email it to your dad so that he can hear how participating you are in class?
I am.
Oh, okay.
I'm also
All right. Anyways,
I'm putting my headphones on.
what we found out too is that what occurs is that the protons attach to the neutrons with something called a strong force. And the way that they showed it in the video is that these strong forces are kind of like bungee cords. So the bungee cords, the neutron is like, the proton sticks to the neutron like with a bungee cord type of a force. What do you know about bungee cords? They stretch, but eventually will they break? Yeah. So that bungee cord type of attraction allows the size to increase a bit, but eventually it breaks. I mean, it can't go indefinitely. You're supposed to be, right? All right. They eventually break.
After this year over YouTube too.
No. We watch them from year to year to year.
Why did you do this year before then?
I have some from previous years. And
Just keep these videos.
all right.
Why did you do this last year?
All right. So here's the important bit. And you see I have some things that are highlighted. I would, if I were you on your notes, or circle it, star it, do whatever. Anything to denote that that's important information. To keep atoms from falling apart, you can't just add protons. You also have to add neutrons. And what they learned was that, you know how the electrons exist in shells, in layers? And I'm sure in physical science in middle school someone taught you that the electron, for an atom to be stable, the electron rings have to be full. The protons and the neutrons also make ring structures. And for the nucleus to be stable, those rings also have to be full. All right, so protons and neutrons make ring structures like electrons, and like electron rings, proton and neutron rings must also be full to be stable. So, electron shells have to be full to keep an atom from reacting to another one. Nuclear rings have to be full to keep that atom from breaking apart and being radioactive. N to the 0 power, yeah. So that superscript denotes the charge.
Why does it smell like green apple? Is that a direct thing? Yes. It smells like green apple.
Man smells. I don't know much about it.
What, Laura? Here, make ring structures like electrons.
What's your hair napkin?
Yeah.
Yeah, nice.
Yeah. I think Jay was being very
I was not. That was you. Uranus. It's pronounced Uranus.
You see, inappropriate, you know that? Like, you're recording this, and everyone can see this video. You need
Am I?
You need to stop and take a step back, okay? I don't understand when you get mad at that. Ask me a serious question. What does that mean?
Am I mad? Like,
No,
where?
when I ask what, I can't see the word again. What we meant. It's like, oh, John, you got step back. Get yourself. What was I doing?
Okay, listen seriously. You need to sign up for drama. You are the biggest drama king I have ever met in my life.
Ask me a serious question, dude.
All right, can I move past this? Does everyone got
Answer my
this?
questions now.
What? What's your question?
Over two videos, they go, see Kyle.
Okay, this is not appropriate for this class.
What do you mean, though?
Okay, all right.
I don't even think Kyle. Wait,
Okay.
what is
All right,
it?
so Ken Moody's group, right? Ken Moody, that guy with the mustache, the one that looked like a walrus on the video, all right? It's not that he did these experiments himself. He's just the guy who leads the group. There's a group of scientists that do this. And it's not just anywhere, right? So first of all, particle accelerators, you can't carry one in your back pocket. These are huge facilities, and these experiments cost millions and millions of dollars. And so there's only like one possibility of who can do this, and that's governments, federal governments. So our government has a national light source where they do this at Los Alamos. The Russians have a light source. That guy, Ken Moody, Glenn Seaborg's student, is just a guy who runs the show, all right? He's not alone doing this experiment. He has a whole group of scientists doing this. So his group at Los Alamos National Lab, that's what that says, NATL for national, and the Russians, because they have a group too, made elements 103 to 118. Los Alamos is where they did the first nuclear tests, yeah.
Sure.
Los Alamos is not the Alamo. That's in a different place. Alamo means car rental company. All right. So first of all, they did not make the elements in order. They didn't even try. Okay. They went after number 114 first on purpose, and that's because they figured they would have the most success with that one. Right? When you have a bunch of things to do on a to-do list, what do you go after first? The thing that's going to take the least amount of time, and the thing that you're going to be successful on. Right? You do the hardest first? Man, you're a glutton for punishment, Alex. I don't. I go after the easy stuff first. So that's what they did. They went after 114 on purpose because it was the easiest thing that they thought they could do. You want to get that glory as quick as you can. You want to say, hey, I made element 114.
Did you get a Nobel Prize?
No, it wouldn't be a peace prize. It'd be a prize in chemistry. But I have to look that up. And actually, there was a lot of stink there was a big stink about this work because when the American group published their results, they actually falsified some of the data. And then a couple of years later, the Russians ended up coming up with the real data, and then they got to name the element after their scarcity quota. So it's important that you have two groups doing this because when one group makes it, the second group has to repeat the experiment to confirm it, and vice versa. And that's how they've been working for the last 20, 30
Is
years.
that why it's called like Flavius?
Fluorobium. Yeah. Flavius, I think, is a character in a Shakespeare play. All right. That's pretty good, though. All right, so element. Element 114 was made like this. They took calcium and plutonium. So rather than shooting just protons at uranium, they took two smaller atoms and folded them at each other. All right? And so why are these a good combination? So I put these numbers in the wrong place. I put them in the superscriptive position, but they should really be in the subscriptive position. But that's the atomic number. So the atomic number for calcium is 20. For plutonium, it's 94. What's 20 plus 94? 114, right? So they were trying to come up with the right combination of elements that would add up to give you the right number of protons. And it's not just that they have the right number of protons, but they also have the right number of neutrons, okay? So element 114 was expected to have the correct number of protons and neutrons to fill those rings in the nucleus and to be stable. So these two particular elements had just the right combination of protons and neutrons both to give you full rings in the nucleus. And so that's why they went after that one first. Yeah, it really should be PU94 on the bottom left. But I just put it in the wrong place. Yes, Patrick? Well, right, because when they make these things, they only make like 1,000 atoms at a clip, right? So it's such a small number of atoms, it's enough for you to confirm that you made it, but not enough to actually hold in your hand, look at it. No, you really don't. You can guess, based on what family it falls in, that it probably, like it falls right underneath lead, so it might behave like lead. So it'd be something that's super dense and malleable. But you really don't know, because 1,000 atoms you can't hold out of your hand. You can't see it, you can't feel it, you can't poke it, you can't do anything with it. And so what they're hoping to do is to scale up these experiments in order to do that. And if you could see it, and you could confirm that it did behave like lead, then you have absolutely proved the periodic law. Okay?
Sure.
All right, any other questions? Fantastic. Let me stop the recording. I think we got enough of Keanu's mouth in there.